Hello, today I'm going to work through a set of questions that you might typically get in an A2 level physics exam on gravitational and electric fields. So let's just begin with the formulae that we're going to need for this section. Firstly, force is equal to mass times gravity, that's close to Earth. More generally, force is equal to the gravitational constant g times the mass of one object times the mass of the other, that's capital M and little m, divided by the distance between them, that's r squared. And we often put a minus sign in front of that to indicate that the force is an attractive force. So the force is, as it were, between the Earth and the Sun. The force from the Earth to the Sun goes towards the Sun, whereas r, the vector that we're measuring the distance, moves from the Sun outwards. So in other words, the force goes inwards, but the measurement of the distance goes outwards. So to reflect the fact that they are in two different directions, the force is in the opposite direction of the distance, r, we put a minus sign. We can see that if F equals mg, the first formula, then g is equal to capital G, capital M over r squared from the second of the formulae. The gravitational potential energy is minus capital G, capital M, little m over r. And you'll see that if you differentiate the gravitational potential energy with respect to r, you will get the force. Then V, which is the gravitational potential, is essentially the gravitational potential energy per unit mass if we regard little m in the formula above as being the test mass. Then the gravitational potential is equal to minus capital G, capital M over r. Then we come on to the Coulomb force, which is a force that exists between two charged particles, Q1 and Q2, and that force is Q1 Q2 divided by 4 pi epsilon naught r squared. The electric field is the force per unit charge, which is Q1 over 4 pi epsilon naught r squared. The electric potential energy is Q1 Q2 divided by 4 pi epsilon naught r, and again you'll notice that if you differentiate the potential energy with respect to r, you get the force. The electric potential V is essentially the electric potential energy per unit charge, so it's Q1 over 4 pi epsilon naught r. The electric field is measured in volts per meter, so it's volts divided by, or V divided by the distance. But we also showed that the electric field is the force per unit charge, so it's F over Q. So F over Q equals V over D, which means you can show that VQ is equal to F times D, but force times distance is work. So voltage times charge is work. And finally, when we do have to use the gravitational constant, capital G is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Question 1. The Earth's radius is 6.4 times 10 to the 6 meters, and the gravitational acceleration on the Earth's surface is 9.81 meters per second squared. We are asked to find the mass of the Earth. Well, we'll recall that near the Earth we can say that the force between any test mass on the Earth and the Earth itself is going to be mg, where m is the mass of the little test mass. Or more generally, we can say that the force is equal to the gravitational constant times the mass of the Earth times the test mass divided by the distance between the two. And you can see that if you cancel out, you can say that mg is equal to gmm over r squared on the surface of the Earth, because that's when this applies. The test mass cancels, and thus you get that g is equal to capital G m over r squared, where r, of course, is the radius of the Earth. It's the distance essentially from the centre of the Earth to the surface where g applies. Rearranging this formula, you get that the mass of the Earth is equal to g times r squared, that's just bringing the r squared up there, divided by capital G. And now all we have to do is to substitute in the values in order to get m. So m will be g, which is 9.81, times the radius squared, which we were told was 6.4 times 10 to the 6, all squared, divided by g, and we said at the beginning of this video that we usually take g to be 6.67 times 10 to the minus 11. And if you multiply that out, you should get that the mass of the Earth is 6.02 times 10 to the 24 kilograms. Question 2. The mass of the Moon is 7.43 times 10 to the 22 kilograms. Its radius is 1740 kilometers. We're asked to find three things. First, the gravity on its surface. Secondly, the potential energy of a 10 kilogram mass, which is 20 kilometers above the surface. And thirdly, the velocity of that mass if it were to fall to the surface. We use the formula that G is equal to Gm, capital G, m over r squared, to find the gravity on the surface, where r, of course, will be the distance from the centre of the Moon to the surface, that is its radius. And that's going to be equal to G, which is 6.67 times 10 to the minus 11, multiplied by the mass of the Moon, 7.43 times 10 to the 22 kilograms, divided by r squared. Well, the radius we were told was 1740 kilometers, so don't forget that has to be first converted to meters, and then the whole thing has to be squared. And if you put that into the calculator, you should get that G on the Moon is 1.64 meters per second squared. And that is about a sixth of the value of that on Earth, where it would be 9.81 meters per second squared. Secondly, we're asked to find the potential energy, E, which is equal to minus Gmm over R. Now, of course, energy is a scalar, so in a sense the minus sign is irrelevant here. So I'm just going to calculate the potential energy without worrying about signs. So G is 6.67 times 10 to the minus 11. The mass of the Moon, capital M, is 7.43 times 10 to the 22. And the mass of the object was 10 kilograms. And then we divide that by the radius, which is going to be 17. Now, it's not 1740 anymore, because the mass is 20 kilometers above the surface. So now R is the radius of the Moon plus the 20 kilometers above the surface, so that becomes 1760. And of course you've got to convert that to meters. And if you put all that into your calculator, you should find that that comes to 2.82 times 10 to the 7 joules. The third question is, what would the velocity be if that mass were to fall to the surface of the Moon? Well, what would happen, of course, is that potential energy would all convert into kinetic energy, and so effectively the kinetic energy would be a half mv squared, and that would be that amount there. So now we've got that half of m, well, remember the mass was 10 kilograms, so half of m will be 5, times v squared, which is what we're trying to find, is equal to 2.82 times 10 to the 7, which means that v squared is equal to 2.82 times 10 to the 7 over 5, and that equals 5.64 times 10 to the 6, and that's v squared, which means that the velocity is equal to the square root of that, which is 2.37 times 10 cubed meters per second. So, if a 10 kilogram mass 20 kilometers above the surface were to fall to the Moon, when it hit the Moon it would be travelling at 2,370 meters per second. Question 3. A satellite is orbiting the Earth 50 kilometers above the Earth's surface. We're asked to find the period of rotation and its velocity. Well, first let's just derive the formulae that we're going to need to find out what the velocity and the period are. We recall that if we've got a satellite orbiting the Earth, then the centripetal force, which is keeping it in orbit, must be being provided by the gravitational force. So essentially the centripetal force, which we'll call Fc, is going to be mv squared over r, where v is the orbiting velocity that in fact we need to find, and that is going to equal the gravitational force, which is gmm over r squared, where r in each case is going to be not only the radius of the Earth but plus the distance that the satellite is above the Earth. M is the mass of the Earth, little m is the mass of the satellite, and g is the gravitational constant. And that will reduce to giving you that v squared, because the m's cancel out. So v squared, and of course one of the r's cancel, v squared is equal to gm over r, which means that v is equal to the square root of gm over r. And of course we know what g is, we know the mass of the Earth, we know the radius of the Earth plus the height of the satellite, so we're going to be able to find out what v is. Let's just first get the formula for t. We know that the period is going to be, which is the time for one cycle, is going to be the distance that that satellite travels in one cycle, which of course is around a circle, so that's going to be 2 pi r, where r is the distance from the centre of the Earth to the satellite's position. So that's going to be the radius of the Earth plus the height above the Earth's surface that the satellite is orbiting, divided by the velocity of the satellite. So time is going to be distance divided by speed. So once we've found the velocity here, we'll be able to substitute that in there. So let's first of all just do the pure maths. The velocity is the square root of gm over r. Well, that's going to be 6.67 times 10 to the minus 11. That's g. The mass of the Earth we've been given as 5.98 times 10 to the 24 kilograms. This is all square root, so that's gm, divided by r. Well, r is the radius of the Earth, which is 6,400 kilometres, plus the 50 kilometres above the Earth's surface that the satellite is orbiting. So that's going to be 6,450 kilometres, so we must convert that to metres. And then if you just do the straight calculation, you should find that that comes to 7.86 times 10 to the 3 metres per second. So the velocity of this satellite is 7,000 metres per second. And then using this formula here, we can just find what t is. T is going to be 2 times pi times the radius, which again is going to be this value, 6,450 times 10 to the 3. That is, just to remind you, the Earth's radius plus the distance above the Earth that the satellite is travelling, divided by the velocity. Well, that's what we just established, that's 7.86 times 10 to the 3. And again, if you put that through your calculator, you should find that that comes to, that will be in seconds, it's 5,154 seconds, and that is very roughly 1.43 hours. So the satellite orbits once every 1.43 hours. Question 4. How far above the Earth's surface must a geosynchronous or a geostationary satellite orbit? Well, the point about a geosynchronous or geostationary satellite is that its period of orbit, so the satellite's period of orbit, must equal the period of orbit of the Earth, so that the satellite always remains above a particular point on the Earth's surface, more accurately above the Earth's equator at all times. So it appears to be stationary. Well, what is the Earth's period of rotation? Well, it rotates once every 24 hours. We don't need to be more accurate than that for this purpose. So it's 24 hours times 3,600 seconds, which is actually 86,400 seconds. So the period of the Earth's rotation is 86,400 seconds. Consequently, so must that be of the satellite. Now you may recall from question 3 that we derived that the velocity of a satellite would be the square root of gm over r, and that the period of rotation would be 2 pi r divided by v. So now if you take t as 2 pi r divided by v, that is divided by the square root of gm over r. And if you simplify that, well, effectively what you do is you square both sides of that equation, and that gives you that t squared is equal to 4 pi squared r cubed over gm. And we are trying, at least initially, to find r, the distance above the centre of the Earth that the satellite must orbit. So we're going to rearrange this formula for r cubed, and that's going to equal t squared gm divided by 4 pi squared, where remember g is the gravitational constant, m is the mass of the Earth. R, just to remind you, is the distance from the centre of the Earth to where the satellite is. We actually need the height above the Earth's surface, so we're going to have to do a slight adjustment. But for the moment, let's just work that all out. If you calculate all of this, you'll find that that means r cubed is equal to t, which we established earlier in seconds is 86,400 seconds. So it's going to be 86,400 squared, that's t squared, times g, which is 6.67 times 10 to the minus 11, times m, the mass of the Earth, which is 5.98 times 10 to the 24. And that is all going to be divided by 4 pi squared. And if you put that into the calculator and take the cube root, then you'll find that r is equal to 4.23 times 10 to the 7 metres. Now remember, that is the distance from the centre of the Earth to the satellite. We have been asked what is the height above the Earth's surface, so therefore we have to take this distance r, 4.23 times 10 to the 7, and subtract from it the radius of the Earth, which is 6.4 times 10 to the 6 metres, and that gives us a total of 35900 kilometres. Sorry, 35900 kilometres, which is about 22,000 miles. So all geosynchronous or geostationary satellites must orbit 22,000 miles above the Earth's surface. Question 5, we have a 1500 volt DC source which is applied across two parallel plates which are 4.5 millimeters apart, and we're asked to find what is the electric field between the plates. And here we just say that the electric field is equal to the voltage divided by the distance. It's going to be measured in volts per meter, and that's simply going to be 1500 divided by the distance, which is 4.5 times 10 to the minus 3 meters, and that's going to be 3.3 times 10 to the 5 volts per meter. Question 6. We have an alpha particle which is being fired at a thin gold foil. As it approaches one gold atom, it is deflected, and its closest distance of approach is 5 times 10 to the minus 12 meters. We're told that gold has a nucleus with 79 protons, so effectively it will be 79 times the charge of an electron. And we're told that an alpha particle has a charge of twice that of an electron. It has 2 protons. And we're asked to find the force between them and which direction that force operates. Well, we can do the direction straight away. These are two like charges, and like charges repel. So the force between the two is going to be a repulsive force. They're going to push one another apart. In fact, the gold atom won't move very much at all. It's the alpha particle that is going to be deflected and pushed away. So the force is a repulsive force, but now we need to find its magnitude. We are told that you can regard 1 over 4 pi epsilon naught as equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared, which gives us a bit of a clue as to which formula we're going to use. We're going to use, of course, Coulomb's law. F is equal to the charge of one particle times the charge of the other particle divided by 4 pi epsilon 0 r squared, where r is the distance between them. So effectively what we've got is 79 worth of charge here and 2 worth of charge here. But what is that charge value? It is equivalent to each charge value is that of an electron. So we've got that force is equal to, well, let's take the alpha particle will be 2 times the charge on an electron, which is 1.6 times 10 to the minus 19 coulombs, multiplied by Q2, which is 79 electrons worth. So that's times 1.6 times 10 to the minus 19. That's Q1, Q2. Now it's 1 over 4 pi epsilon 0, but we're told that 1 over 4 pi epsilon 0 is this value here. So this continues times 9 times 10 to the 9. This is all in the numerator. And then that is going to be divided by r squared. And r, we were told, the closest distance of approach was 5 times 10 to the minus 12 meters. So r squared is going to be 5 times 10 to the minus 12, all squared. And now it's just a case of putting that into the calculator, and that comes to 145 times 10 to the minus 5 newtons. Question 7. We're asked to find the gravitational and electrical forces between two electrons which are 10 to the minus 10 meters apart. That is approximately 1 atom's width apart. The two formula we're going to use, of course, are for gravity. That is, the force is G mm over r squared, where G is, of course, the gravitational constant. These are the masses of the two electrons, so they will be the same, and r is the distance between them. For the electric field, we're going to use, the electric force, we're going to use Coulomb's law, which is that F is equal to Q1, Q2, divided by 4 pi epsilon naught r squared, where again Q1 and Q2 will be the charges on the two electrons. So let's do the gravitational force first. That's going to be G, which is 6.67 times 10 to the minus 11, times the mass squared, essentially, because it's two electrons. So the mass of an electron is 9.11 times 10 to the minus 31 kilograms. You will usually be given that information, and that has to be squared, divided by the distance between the two, which I said was 10 to the minus 10, all squared. And that is equal to 553 times 10 to the minus 53 newtons. An incredibly small force. And that, of course, will be an attractive force between the two. Now we do the electric force, or the Coulomb force. Well, we've been told before that 1 over 4 pi epsilon 0 is equal to, or can be regarded as 9 times 10 to the 9. So that's taken care of the 1 over 4 pi epsilon 0. So now we need to go to Q1, Q2, which is the charge on the two electrons. Well, that's 1.6 times 10 to the minus 19 coulombs squared. You'll usually be given that information too. Divided now just by the distance between them squared. Well, the distance was 10 to the minus 10, and that's squared. And that's going to be in newtons, of course. And if you calculate that, you should get 23 times 10 to the minus 9 newtons. And that, of course, will be a repulsive force because it's between two like charges, the two electrons. So if you compare the two, you've got 23 times 10 to the minus 9 repelling, 553 times 10 to the minus 53 attracting. Huge orders of magnitude between the difference. The Coulomb force is massively greater than the gravitational force. Question 8. We have a 2000 volt supply across a parallel plate, and we have an oil drop which is suspended between the two. The mass of the oil drop is 2 times 10 to the minus 6 kilograms, and the distance between the plates is 5 centimeters. We're asked to find the charge on the oil drop. Well, the reason the oil drop is suspended and not falling is because there must obviously be an electric field operating between the plates. What we do know is that the gravitational force, which is tending to pull the oil drop down, must be exactly balanced by the electric force acting on that oil drop, which is acting upwards, and the two are equal, and that's why the oil drop is suspended. Well, what are those two forces? Well, the gravitational force acting downwards is simply going to be mg, the mass of the oil drop, times g, gravity. What about the force acting upwards? Well, we know that the electric field is equal to the force per unit charge, and it's also equal to volts divided by distance. So consequently, we can get that the force is equal to VQ divided by distance. So those are the two forces, and they must be equal, which means that mg must equal VQ over d. And on that basis, Q, which is the value of the charge, which is what we're trying to find, is going to equal, by rearranging that formula, mgd divided by V. And now it's just a case of substituting in the values. We were told that the mass is 2 times 10 to the minus 6 kilograms. We know that gravity is 9.81. And we know that the distance between the two plates was 5 centimeters. So that's going to be 0.05 meters. And that's going to be divided by the voltage, which you may recall was 2000 volts. And if you put all that into the calculator, you should get that that is 49 times 10 to the minus 11 coulombs. Question 9. We're asked to calculate or derive the formula for escape velocity. Well, the point about escape velocity is that if you can give an object an initial velocity that is sufficiently high, then without any further force and with no engines, it will completely escape the gravitational clutches of the planet or whatever you're escaping from. The point is that, of course, the gravitational force is infinite because it is simply 1 over r squared. So you don't escape gravity until you have reached an infinite distance away. So let's say we're trying to escape from the Earth. Here is the Earth. And we're going to escape with an initial velocity v. Gravity will slow us down all the time. But if we reach 0 before we get to infinity, gravity will pull us back. So we must reach 0 only when we get to infinity. So at infinity, velocity equals 0 and kinetic energy therefore equals 0, since that's half mv squared. But at infinity, the potential energy is equal to 0 too. So the consequence is that kinetic energy plus potential energy is equal to 0, and since energy can be neither created nor destroyed, that must be the case at every point along this journey. If you add the relative kinetic energy, which of course will be reducing all the way because velocity is reducing, to the potential energy, which is increasing all the time, then you get 0. How can something be increasing if when it gets to infinity PE is 0? Well, of course, the reason for that is that potential energy is a negative value. So kinetic energy at any point is a half mv squared. Potential energy at any point is minus gmm over r. And we'll go from minus whatever the value is up to 0 when it gets to an infinite amount an infinite distance away. And consequently you get that the sum of the two, half mv squared minus gmm over r, is equal to 0 at all points in that journey. So if you take the position when you are actually on the surface of the Earth, then you get the position that, look, the m's cancel out, and you get that v squared, which is what we're looking for, is equal to 2gm over r, where r is obviously the radius of the Earth in this case, and so v is equal to the square root of 2gm over r, which means the escape velocity must equal 2 times g times the mass of the Earth divided by the radius of the Earth. And you may like to substitute values in for that. You should find that the escape velocity comes to 11 kilometers per second. And finally, question 10, we're asked to show why Kepler's third law is true, that the period of rotation of, say, a planet squared is proportional to the radius from the Sun cubed. We're going to assume a circular orbit, and we will therefore say that the centripetal force that keeps the planet in orbit is provided by the gravitational force, so we get that the centripetal force, which is mv squared over r, is going to be provided by the gravitational force, which is gmm over r squared, where m in this case will be, capital M is the mass of the Sun, small m is the mass of the planet. Now you'll notice that the small m's cancel out, and that will give us that v squared is equal to gm over r, because of course one of the r's cancels as well. We also know that the period of rotation will be the distance divided by the speed, which is 2 pi r. That's the circumference of the orbit, divided by v, the velocity, so that gives you the time for one orbit. Square that, and you get t squared equals 4 pi squared r squared over v squared. But v squared we've already calculated is gm over r, so now we can substitute that. We get t squared is equal to 4 pi squared r squared divided by v squared, which is gm over r. And consequently t squared is equal to 4 pi squared r cubed divided by gm. Now this term here is a constant if you're talking about going around the Sun. 4 pi g, m is the mass of the Sun, and consequently you're left with t squared is proportional to r cubed.